The Science of Everyday once again, and from the physics department at the University of Guelph, once again we have Tom Kehn.
Good morning.
And Professor Ernie McFarland.
Good morning.
So guys, you got some magnets here, I understand, and some motors.
Yeah, we've got some really interesting electricity stuff, and also some, well, you'll see a really strong magnet, and we're going to see some of the connections between electricity and magnetism.
I understand this is the world's simplest motor.
The world's simplest electric motor. So on the bottom, we've just got a battery.
Yeah.
And of course, it's got, two terminals. And one of the battery terminals is connected to this vertical metal piece here, and the other terminal connected to this one. And there's a little disc magnet in the middle.
Okay.
And then we've got a coil of wire with one end of the coil coming off on one side and the other end coming off on the other side. And so now I'm connecting that here to those two terminals, and we're now starting to get an electric current flowing through those coils.
All right.
And I'm just going to give this a little spin to get it going. And now you can see it's spinning around and around and around. There's the world's simplest electric motor.
And it just keeps going.
It just keeps going. So the basic physics behind this is when you have a current flowing, and if there's a magnetic field there, the electric current experiences a force. And in this case, since we've got a coil,
right,
we can actually talk about the coil experiencing a torque. That's the twisting effect of a force.
Yes.
And we end up with this thing just continuing to spin around. And I mean, this is the principle behind all electric motors. You get current going through a coil, there's a magnet there of some sort, and you get this spinning, 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 spinning.
All right.
And
now, sorry, we let that go.
Okay, we'll just let that spin.
And we have got a bigger magnet here.
Yeah, we've got a very strong magnet here, and we've got a piece of iron kind of between the poles of this magnet. And maybe, Tom, you can just kind of demonstrate how strong this magnet is.
Okay, that's a good... There we go.
Okay, so there we got a really strong magnet. Okay, so I just want to indicate this is an extremely strong magnet. And here, I've got a piece of copper at the bottom of a piece of brass. And I just want to emphasize, first of all, that this copper is not attracted magnetically to this magnet. If it were, it'll clang and be really stuck on it.
It's just metal.
Just a piece of metal. It's a metal conductor, but not magnetic.
Right.
And far away from the magnet, I just want to indicate how this little pendulum will work. It swings along quite easily, not a lot of friction. You see it swings back and forth, many, many times. But now, I'm going to move it over to here.
For another demonstration, yes.
And I'm going to have it swing between the poles of this very strong magnet.
Right.
Now remember, over here it swung very easily. Let's see what happens now. Okay? Well, you see it got through about, what, one and a half swings or whatever.
Couple there, yeah.
What happens is this thing, as the copper conductor swings through this strong magnetic field, electric currents are induced or created inside this piece of copper. And they swirl around. This is not part of an electric circuit. They swirl around like eddies in a river, and they're called eddy currents.
Okay.
And just as over here with our little motor, when you've got a current and a magnetic field, there's a force.
Yeah.
And in this case, the force acts to break or to slow down this pendulum bob as it's swinging through the magnetic field.
It's like an electric brake.
It's like an electric brake. I haven't heard it called that, but it's sort of a combination electric-magnetic brake or something. So you can see it slows down very quickly. Now, if I could cool this copper down, its electric resistance would get very small. And then if it were to swing through the poles of the magnet, the eddy currents that could be created would be very much bigger, and the braking effect would be even more dramatic.
And I bet you can show me a cooled down.
That's right. We've got a cooled down pendulum here.
How cold is it, Ernie?
It's very, very cold. It's been sitting in liquid nitrogen.
It's so cold.
It's been sitting in liquid nitrogen, so it's 200 degrees below zero. So again, the eddy currents induced will be very much bigger. And let's let this swing and see how many times it swings.
Hey!
That stops
pretty quick.
So this electric magnetic brake just works dramatically well.
So the cold makes the electric
electric resistance of the piece of copper very small, and so that means the eddy currents that can be created can be very big, and that means the effect can be very big. I'll swing this one more time.
Yeah, let's watch that. That's it.
Just stops dead.
Now, I'm prompted to ask, what's the everyday application for this kind of technology?
Well, I imagine many of your viewers have been to Canada's Wonderland or places like that. And I know at Canada's Wonderland, there's something called the drop zone.
Yeah.
And you might wonder how the people can stop as they're going down from such a high speed. And
I wonder how they get on the thing in the first place.
Well,
but yes.
yeah, I don't like to get on those things. It's eddy current braking or electric magnetic braking. On the bottom of those cars are big magnets. And as those cars go zooming down toward the bottom of the ride, beside the cars are big, I believe they're copper plates. And so eddy currents get induced or get created inside those copper plates because you've got this magnet moving past quickly. And now in that case, the braking is not on the pieces of copper, which are stationary, but on the magnets, which are attached to the cars.
Now, Tom, you have another demonstration for this, a mini drop zone right here.
A mini drop zone right here. We have an
There's
ordinary.
the tape. Sorry, there's the,
yes,
the drop
there we
zone, the
go.
slow motion, and the...
And I'm glad I'm not on that.
Yeah, and it's kicking in right about there.
Yeah, so the braking there is not friction or anything like that.
Right.
It's the interaction between the magnets on the bottom of the cars
Always wondered about that.
and those copper plates. So it's quite remarkable.
Right. Sorry, Tom. So you've got...
So we've got here an ordinary copper pipe,
Yeah.
non-magnetic,
Right.
and a couple of pellets. This one is non-magnetic. If I drop it through the pipe, this falls through
Okay.
the other side. I now have another pellet that is magnetic. You can see
Okay.
I can pick up a toonie with it.
Yes, yes.
And we'll drop it through the pipe. And it's
Nothing.
like drop zone. It takes a while.
Oh, but it does come through.
It does come through.
But it's not because of the magnetic thing.
That's right,
It's because of those
the
eddy currents.
Exactly. And if you can get a couple of pellets such as these in an ordinary pipe, you can do this at home.
Fantastic. Gentlemen, thank you once again.
Thank you.
You're welcome.
Got a charge out of that one.